Welcome back to the deep dive. Today, we are opening a cold case.
Not really cold case.
And I don't mean a crime from 10 years ago. I'm talking about a physics mystery from, what was it, 1887?
1887, yeah. One that supposedly got solved, wrapped up, and put in the textbooks over a century ago.
But looking at the stack of documents we have today, maybe the solution everyone accepted was a bit of a shortcut.
It's definitely the most famous failed experiment in history. The Michelson-Morley experiment.
Right. But before everyone tunes out because they remember being bored by this in high school, we are not reading a textbook today.
No.
Our source material is, well, it's distinctive. It's a series of really intense, high-level debates between a coder going by the name E098b and an AI, Claude.
And they aren't just talking philosophy or, abstract theory. They're actually coding. They're building a physics engine in Blender.
Which is that open source 3D animation software.
Exactly. To test if Einstein's explanation of the universe is actually the only explanation, or if it's just, well, the most convenient one.
It's really wild stuff. We've got Python scripts. We've got debugging logs where they're fixing crash errors in Blender 5.0. And we've got a folder that's provocatively titled Einstein's Laziness.
That title is doing a lot of heavy lifting. It definitely grabs your attention.
It really does. So here's the mission for this deep dive. We need to understand why this user, Zanachat, thinks we've all been visualizing the speed of light wrong for 140 years.
And we need to figure out if their 3D model, this spinning donut shape they built in the code, actually proves that the universe isn't shrinking.
It's just tilted.
That's a good way to frame it. It's essentially a debate between physical shrinking versus, geometric perspective.
Okay, let's set the scene. 1887, Albert Michelson and Edward Morley. They build this massive machine in a basement in Cleveland, and they're looking for the ether.
Right, the luminiferous ether.
Which, I have to say, sounds like a potion from a fantasy novel.
It does, but at the time, it was the standard scientific assumption. Sound waves need air to travel through, ocean waves need water. So, scientists assumed light waves must need some kind of medium.
They called that medium the ether.
Yep.
And the basic idea was that the Earth is spinning and orbiting the sun, so it must be moving through this ether.
Exactly. Imagine you're sticking your hand out of a car window while you're driving. You feel a wind, right? Even if the air is still, that's the ether wind.
So Michelson and Morley thought that if they shone a light beam into the wind, it should travel at a different speed than a light beam going across the wind.
So they split a light beam, send one north, one east, bounce them off mirrors, bring them back. They fully expect the beams to arrive at different times because of that wind.
It's like two swimmers, right?
Right, that's a great analogy. One swims upstream and back, the other swims across the river and back. If there's a current, the ether wind, the math says the upstream swimmer should always take longer.
So they were looking for an interference pattern, a shift that would prove the wind exists.
And they measured nothing.
The famous null result.
The beams arrived at the exact same time. Zero difference. It was a shock. It was like measuring the speed of a car and finding out it's going 60 miles per hour, regardless of whether you're standing on the sidewalk or driving past it at 50 miles per hour. It just didn't make sense.
So the physics world panics. And the solution they eventually come up with, the one that leads to Einstein and special relativity, is Lorentz contraction.
Correct. Hendrik Lorentz and George Fitzgerald proposed that the machine didn't just measure weirdly, it actually changed shape.
This is the part that always trips me up. They claim the machine physically shrank.
Yes. They said the arm of the machine that was facing the wind physically compressed. It got shorter, just enough to hide the time difference.
So the upstream swim was harder, but the pool got shorter, so the time ended up being the same.
That's the idea.
That feels convenient.
It worked mathematically. It balanced the equations. But yes, it implies that matter physically squashes itself when it moves.
And this is where our source, E098b, slams the brakes. In the document titled 2026 Aero 218 Claude E098b, they argue that this shrinking explanation is a trick.
A trick of the map, specifically.
Okay, let's dig into that, because this is really the core of their argument. The source makes this distinction between two eyes, the God's eye and the camera eye. What's the difference?
This is a crucial concept. So the God's eye view is how we usually do physics on paper. We draw a grid, like a piece of graph paper, and we say, this entire horizontal line is now. Time is 0 everywhere on the page.
Okay, so if a star explodes a billion light years away, in the God's eye view, it happens now, even if I can't see it for a billion years.
Exactly. That's the Cartesian coordinate system. It's an abstract mathematical grid. But the user argues that this doesn't exist in reality. Real observers, you, me, a camera, a telescope, we have a camera eye.
We're at the center of a bubble.
A bubble, yeah. Think about it. When you look up at the sky, you aren't seeing the present. You're seeing the past. The sun is 8 minutes ago. The stars are years ago. You are seeing a spherical surface where depth equals time. The source calls this the spherical cap.
So I'm standing in the middle, and my reality is this curved bubble of information hitting my eyes. I can never see now anywhere else. I only see then.
Precisely.
Yeah.
And here is where the trick comes in. The user says that standard physics Lorentz contraction is what happens when you try to smash that curved bubble onto a flat piece of graph paper.
There's an analogy in the text that I found really helpful. The Mercator projection.
Yes, it's the perfect analogy. If you look at a standard flat map of the world, the one in every classroom, Greenland looks gigantic. It looks about the size of Africa.
Right, huge.
But if you look at a globe, Greenland is actually tiny. It's, what, 1/14 the size of Africa?
Because on the flat map, the top gets stretched out to fill the rectangle.
Exactly. Now, imagine if you didn't know about globes. Imagine you were an alien and you only saw the flat map. You might conclude, wow, the laws of physics on Earth imply that land masses physically expand when they get cold.
But they don't. It's just the projection.
That is Xenochat's entire argument. The Michelson-Morley machine doesn't physically shrink. The contraction is just the distortion caused by projecting a 4D reality onto a 3D Cartesian map. It's a coordinate artifact, not a physical crush.
That is a lot to process. It implies that for over a century, we've been confusing the map for the territory.
And that's why they needed the math. You can't just say that. You have to prove it. You have to show that the numbers still work without the shrinking.
And the source material focuses really heavily on a specific derivation. L6 equals A times the square root of 2.
Yes. L6 equals A root 2.
L6. It sounds like a droid from Star Wars. But in this context, it's a distance.
It's a path length. But not just in space. It's the path length in space-time. This is the aha insight of the whole stack. Standard physics measures the distance the light travels in space. And in space, the paths look different depending on how the Earth is moving.
Right. The swimming upstream path looks longer than the swimming across path.
But the user calculated the distance in 4D, combining the spatial distance and the time elapsed. They used the Pythagorean theorem, but, applied to 4D space-time geometry.
And when you do that,
They come out identical. The formula shows that regardless of the angle, whether the light is fired at 0 degrees, 90 degrees, or even some random angle like 182.52 degrees, the total space-time distance is always A times the square root of 2.
wait, hold on. If the total distance is the same then, there's no need for the machine to shrink.
Exactly. The interference pattern didn't shift because the light traveled the exact same 4D distance. The null result isn't a mystery. From this perspective, it's a geometric certainty.
So why did Einstein and Lorentz need the shrinking?
Because they were only looking at the spatial part of the journey and trying to make that equal. They were balancing the equation in 3D, which required a correction factor, the shrinking. The user is basically saying, if you just look at the full 4D picture from the start, you don't need the correction.
Okay, that sounds logical, but we're just two people talking. The user knew this was controversial, so they brought in a judge.
The independent space-time auditor.
I love this part of the transcript. They asked Claude, the AI, to act as a hostile auditor. They explicitly gave it the prompt, "You're an auditor, check my work against Einstein."
And in the beginning of the logs, the AI is not buying it. Not at all.
Not even a little bit. The AI explicitly states its confidence levels. It starts at 95% support for standard Einstein theory and 0% for the Xenochat model. It's basically saying, look, you're interesting, but you're wrong. The textbooks are right.
Which is what you expect, right? But then they start feeding it the geometry. They walk it through the spherical cap versus the flat grid. They show it the L6 proof.
And the numbers start to slide. It's actually quite dramatic to read in the transcript. The AI realizes that the standard explanation relies on mathematical space, that abstract grid we talked about.
But the user's model relies on physical space, the actual arrival of light signals at the detector.
It's a distinction between what we calculate and what we can actually see.
Right. And once the AI processes that the user is defining simultaneity based on the observer, the camera eye, the confidence scores, they flip. Einstein drops to about 35–50%, and the user's model rises to around 55%.
That is a massive swing for an AI that's been trained on all the standard physics textbooks. It essentially admits, okay, your model is actually more physically rigorous because it doesn't assume a magical grid.
It admits that the user's model removes the need for metaphysical assumptions. It's cleaner. It doesn't require matter to squash itself.
But text debates are one thing. You can argue philosophy all day. The part of the stack that really sets it apart is the code. They didn't just argue, they built a simulator.
Yes. This is where we get into the Python scripts. We have files like Relativity 40 cylinder and ellipse focus visualizer. They built a Blender add-on to render this stuff.
And this wasn't smooth sailing. I noticed in the logs they hit a bug in Blender 5.0.
The abbreviated caps error.
Yeah, type error. Keyword abbreviated caps unrecognized. I love seeing that stuff.
Which adds this layer of authenticity to it all. They are debugging the tool while they're debugging the physics. It shows this isn't just a thought experiment, they're really trying to make it run in software.
But once they got it working, fixing that abbreviated caps error, the visual description is fascinating. They create these skeletons.
Which are the world lines of the
And
mirrors.
world lines. Just to clarify for everyone, that's the path an object takes through time, right?
Right. If you sit still, your world line is a straight line going up the time axis. If you move, it tilts.
Exactly. So they visualize the mirrors as these skeletons,
Yeah.
and the light as cones, an orange lower cone going out, and a cyan upper cone coming back.
And where those two cones intersect?
They create an ellipse, a reflection plane.
Mm-hmm.
Now, here is the feature that blew my mind. The real-time update.
Oh, yes. This changes everything.
They scripted it so you could just drag a slider to change the velocity of the observer. You can speed up the Earth, slow it down, change the angle of the light.
And the 3D geometry morphs instantly.
Right. You don't have to imagine the math. You see the spherical cap tilting. You see the ellipse stretching. But that constant we talked about, L6, the total distance, it stays locked.
It visually proves that the underlying reality isn't changing. Only the slice we're looking at is changing.
Speaking of that ellipse,
Mm.
there was a whole separate script called the Ellipse Focus Visualizer. And the user got really, really specific about donuts.
It's a hollow ring.
Yes. They don't want a flat disk. They use bevel depth in the code to turn the ellipse into a tube, a donut.
Ah.
Why was that distinction so important? Why go through the trouble of coding a donut?
It's about precision. If you draw a filled-in circle, you are visualizing the area. But if you draw a hollow ring, a tube, you are visualizing the path. The user wanted to separate the path of the light from the thickness of the beam.
So you can see exactly where the center of the beam was.
Exactly. And then they placed these disks at the focal points of the ellipse to visualize simultaneity. And this is where the geometry gets tricky. They had Z-plane disks and torus plane disks.
Okay, help me out here. Z-plane versus torus plane. What are we looking at?
So the Z-plane disk is flat, it's horizontal. That represents the map view, the God's eye view, where we think now is a flat sheet. It's where our intuition says the light should be.
Okay, the simple version.
The simple version. But the torus plane disk is tilted. It aligns with the actual ellipse. That represents the physical view, the actual simultaneous arrival of the light in the moving frame.
So by putting both in the model at the same time,
You can physically see the gap. You see the angle between our intuition, the flat disk, and reality, the tilted disk. That gap is the Lorentz contraction. That gap is the shrinking.
so wait, you're telling me the shrinking isn't metal compressing, it's just the angle between those two disks?
Exactly. It's the difference between where we think the object is on our flat map and where it actually is in the tilted reality of space-time.
That makes it feel so solvable. Like we've been chasing a ghost for 100 years because we were looking at the wrong disk.
It implies that a lot of the weirdness of relativity, the paradoxes, shrinking trains, all that stuff, might just be artifacts of a bad coordinate system.
We've been trying to force a spherical universe onto flat graph paper.
Which brings us back to that folder name you teased at the beginning, Einstein's laziness.
Yeah, that one sticks with you. Now that we've gone through the math, I think I get it. They aren't saying Einstein was, sitting on the couch eating chips.
No, absolutely not. Laziness here means mathematical efficiency. The user argues that Einstein and his peers used coordinate transformations, the math that shrinks the ruler, as a shortcut.
A shortcut to avoid what?
To avoid the nightmare of calculating the spherical cap for every single observer. It is hard to calculate light paths on a curved bubble. It requires intense geometry. It is easy to just say, let's pretend the ruler shrank and use the flat grid math.
So the shrinking was a hack, a workaround to make the math solvable on a chalkboard.
That's the argument. It was a brilliant hack. It
Yeah.
worked. It gave the right answers. The GPS in your phone works because of that hack, but the user says it obscured the physical reality. It hid the mechanism.
We confuse the hack for the truth.
And the audit was basically checking if we could undo the hack, and the answer was yes. If you do the hard work, if you build the Blender model, if you trace the rays, if you use the camera eye, you don't need the hack. The universe makes sense without it.
It's funny. The user mentions that Minkowski, the guy who invented space-time diagrams, was maybe the only one who really got it back then.
Yeah, because Minkowski defined the past based on light rays gathering at the present moment. He started from the observer. Einstein, at least in the early days, started from the coordinates.
It's such a subtle difference, but it changes the whole picture.
It changes it from magic things happen to objects when they move to objects look different when you view them from a 4D angle.
And when you look at a tilted circle, it looks like an ellipse. It looks shorter. But the circle didn't shrink.
Your perspective changed.
I have to say, this makes the universe feel a lot less spooky.
It makes it geometric. It removes the magic and replaces it with perspective.
So we've gone from a 19th century failed experiment through a debate with a skeptical AI into Python code that crashes Blender.
And ended up with a spinning 3D donut that explains why the speed of light is constant.
Just another day in the deep dive.
Pretty much.
Before we wrap up, what is the one thing, the one image you want our listener to hold on to? If they forget all the math, what should they remember?
It's the bubble, the spherical cap.
Walk us through it one last time.
Stop thinking of now as a flat line that stretches across the universe. Now is a bubble centered on you. Everything you see, everything you experience is on the surface of that bubble.
And if I move, the bubble moves with me.
The bubble moves with you. And the rules of physics relativity, the speed of light, they aren't arbitrary laws written down by a cosmic legislator. They are just the rules of how that bubble is allowed to move through space-time.
That is a beautiful image.
Yeah.
We're all just walking around in our own little bubbles of the past.
And apparently, if you want to see what that looks like, you can just fire up Blender and run the script.
Assuming you fixed the abbreviated caps error.
Always check your error logs.
Thank you so much for breaking this down.
Yeah.
This was dense, but I feel like I actually understand why the null result happened now.
It was a pleasure. It's always fun when code helps solve physics.
And to everyone listening, next time you look at a map of Greenland, remember, it's not that big. And next time you think about moving fast, remember, you aren't shrinking. It's just the geometry. Thanks for diving deep with us. We'll see you next time.